what the goal is today, I'll try to give you some visual idea of what is turbulence, so you can at least understand what we'll be talking about, because later we go to mathematical questions. So essentially I would like to give you some picture of what happens, so that at least it will be a reference for our later discussions when we will start talking about mathematics. So what is mathematically interesting in turbulence? So it means what is turbulence? And then also today we will be talking about very basic things, is like conservation laws and symmetries and so on. So as you remember, we discussed that there are Euler equations which are problematic, and there are Navier-Stokes equations which supposedly not. This week we will be talking about this a bit in more detail. It supposedly are not problematic, but this is one of the millennium problems to prove it. But more or less, expectation is that they're good. So Navier-Stokes equations. Equations, and in principle, we mostly in the most classical body of turbulence, we are talking about incompressible flow. Incompressible fluid. Physically, what is incompressible fluid is like is water, for example. Water under most conditions that you can imagine. Of course, water can also be compressed, but that's almost never happens, at least in our daily life. And then another very typical application to the Navier-Stokes is air, so atmosphere, the air. So air, you think of air is compressible, but in fact air is incompressible when the speeds are not too high. So the air for speeds much smaller than the speed of sound is incompressible. So incompressible model works very well for air when you are very much smaller than the speed of sound, and the speed of sound is something like 343 meters per second. So essentially for everyday life, when the wind is at least 10 times smaller than the speed of sound, then it can be considered to be incompressible. Okay, so the equations of motion, as you remember, so the incompressible version is the shortest. So these incompressible equations and incompressibility plus incompressibility condition. So that equation has two parameters, two physical parameters, which is rho is density, fluid density, and nu is fluid viscosity, kinetic viscosity. Which is, if you remember, is a ratio of dynamic viscosity, which comes from physical properties, divided by density. And since dynamic viscosity is much bigger for fluid, but also the density is much bigger for fluid. So that's why this viscosity is actually rather close for both for air and water. So it's like 10 times different only. So from point of view Navier-Stokes, air and water are not that much different. Okay, and the next is and plus boundary conditions. So you always define boundary conditions. So in covariant conditions is you usually use no slip, which means that the speed is 0 at solid boundary. Okay. So let's consider a specific example and do this analysis. So the specific example that we already considered was a disk, or better, if we go to 3 dimensions, it will be a cylinder. So consider the infinitely long cylinder, let's say of radius r, and on this cylinder you have a flow which is far away, has some certain constant speed, so that you have wind going around the cylinder. Something like this. So these are streamlines, so the wind goes around the cylinder. And its evolution, so the dynamics is described by this function, which is the speed as a function of coordinates and time. So the speed is, in this picture, is 3-dimensional. Coordinates are 3-dimensional. So in this case, you have one more boundary condition. So you have condition far from a cylinder. So you say that u goes to the u infinity. So there is a constant speed far away. So far away, so it's also can be considered as boundary condition. So only not a boundary condition on some given surface, but condition far away. So far away you have this condition. So what are the parameters for this? Parameters for this problem is the parameters. There are several. So you have u, which is I will give it together with dimensions. So the speed at far from at infinity is a dimensional parameter. So the flow speed, flow velocity, so speed far from cylinder. So the speed of the wind. Then we have a radius of the cylinder. So radius. Then the density of the fluid. And finally, viscosity, the kinetic viscosity, it's meter per square per second. So everything depends on 4 numbers. So it turns out that since numbers are dimensional, there is a usual trick how to decrease the number of parameters by considering dimensionless variables. So let's consider dimensionless variables. Dimensionless variables. So dimensionless variables you define just by here there is rather unique way. So you consider dimensionless distance or dimensionless coordinates. So there is quantity of dimension, or you can compute dimensionless coordinates relative to the size of the cylinder. So x by r. Then you can consider the time. So the time, dimensional time, you can, so how you do? So you can get typical time is just the time that flow travels through the distance of the size of the cylinder. So it's U by R. So R by U. So you divide time by this quantity, so it will be R by U in the denominator, so it's flipped. UT by R. Okay, so this is a non-dimensional time. Then U is a rather straightforward way how to dimensionalize U, of course, with respect to the speed of the wind. And then we need also pressure, because pressure also enters. So the new pressure is old pressure divided by, so now if you check dimensions, you will see that dividing by rho U square, you get dimensionless quantity. Okay, we have this quantity, so now, or you can just write it way around, so you can just express physical quantities in terms of dimensionless. And now substitute this into the Navier-Stokes system. Let's see what. Navier-Stokes equation become. So what you do first is du dt, right? The du dt. So you put this u and this t. Yeah? So what you see, there will be coefficient will come out is u squared over r du dt. The same coefficient comes from u grad u, because it's 2 times u plus derivative, so it will be u squared over r. Where everything is now with respect to the dimensionless coordinates. Then gradient of the pressure. So it will be from pressure will give rho u square, and gradient will give, there will be rho at least, and then there is a gradient which gives you what? Well, it gives you r. And then viscous coefficient, so it gives you u divided by r squared. It will be nu u squared. Okay. So now divide everything by this coefficient. And you see what left. So from here you just get derivative. From here you also have only this term. Here also everything cancels, so it's also good. And here what will be left, it will be you divide by u squared, so it will be 1u below. And r will cancel one of the r's. Okay. So the next step is you see that there is only one quantity, one coefficient left. And let's give a name to it. So we give a name to it, but flip it, so put it in the opposite way. And so we multiply the speed of the wind by the size of the cylinder divided by viscosity. So it's called Reynolds number. And so the final equation that let's drop tildes. No? So just remember that we're in the dimensionless coordinates, and what we do, we write Navier-Stokes equation in dimensionless form. So it's just the same equation, but slightly simpler. So there is no nothing divides here p, and then there will be plus Laplacian divided by Reynolds number. And you can also check that the incompressibility condition just remains the same. So this is dimensionless form. Dimensionless Navier-Stokes. And now you can see that what you gain is that boundary condition becomes that U is 0 at the boundary of the cylinder, but boundary of the cylinder is given by now in new coordinates just 1, because after dividing everything by radius become 1. And U become 1, 0, 0 far away. As you go far from a cylinder, the speed goes to 1. So there is no other, so what you see that the only parameter that determines the problem is a Reynolds number. So everything depends only on Reynolds number. So in general, it's a Reynolds number plus geometry of the problem. So if you fix geometry, like in our case, it's cylinder, everything else is defined by Reynolds number. You don't need to know anything. Just one number, just one parameter, and everything is determined by this number. So in general, the Reynolds number is defined as UL over nu. So where U is some typical speed of your problem, L is some chosen typical length, and U is this dynamic viscosity. And you can immediately have many different ideas. For example, if you take the flow in a tube, again, the tube has a radius r. So in that case, Reynolds again becomes, and the speed, average speed is u, the entering speed is u, then Reynolds again become ur over nu. Another problem that you can imagine is the wind around any other object, not necessarily cylinder, for example, around a ball of radius r. Again, Reynolds ur over nu. So essentially, there is one parameter in fluid dynamics that normally, given the geometrical property, the only one dimensionless parameter, which defines what will be the flow. Okay, nothing else. So everything depends on it. So good to understand what is the numbers. So what are the values of this Reynolds number? And actually, the turbulence is mostly about Reynolds number. So typical values of Reynolds numbers. I took it from Wikipedia, so you can just see it with more details. So from smallest to largest. So the small object, which is still macroscopic, so which is flowing in the fluid, is a bacterium. So very important nowadays. So the bacterium I don't know what is the size, maybe microns. So it gives Reynolds numbers. When it flows, the Reynolds numbers of its flow is something like 10 minus 4. So something very, very small. So the next is very small fish. Very small fish already gives you Reynolds between 1 and 10. So already something much bigger. Then the next value corresponds to the flow of the blood when you win, so the flow of the blood in the body. Yeah. Blood flow gives next order, so it's between. Usually varies between 100 to 1,000. The next is the flying ball. So when you throw the ball, you go next. So it's 10, 4, 10, 5. Next order is when you swim. So the swimming person. It gives 10, 6. Then we can go to some very big fishes. So the whale, or big fish, fast fish. Can go to 10, 8. Then you take ship. The normal size ship, it goes to 10, 9. And you can continue. So the atmospheric motion, the cyclone, the size of the cyclone which you have in atmosphere. So it's very important, no? It's weather prediction, where the fluid dynamics is a central question. So it's 10 power 12, and so on. Then you can go to also some astrophysical ideas. For example, some motion within the stars or stars and galaxies, so it goes to much large numbers. So anyway, the conclusion is that usually Reynolds is very high. Not good to say usually, often. So in many cases, Reynolds number is something very big, very big. And what you can see about the Reynolds number is that the Reynolds number is here. It's in denominator. So usually in all our problems, the only number that matters in the equation is very big and stays in the denominator. So in usual situation, what you do with the equation, you say, okay, if I divide by something very big, so that term doesn't matter. So in the zero approximation, I just remove this term, and use these equations. And this term is actually not only, so the denominator is not only very big, but it can be enormously big. So for example, already considering the shape of the atmospheric phenomena, it's 10 power 10. So it's enormously big. You cannot even make any numerical simulations with a number like this. So it's enormously big. So you would like to remove this term, but whenever you remove this term, you are back to the Euler equations. And we know Euler equations has a trouble. So we have here this duality. So we have a term which is, has a very large denominator, and the equations are good, but there is a problem with this term, because there is something in the denominator which is very large and important, and whenever we take it out, we have a problematic equation. So this is how mathematics, very vaguely, how the mathematics, where the mathematics comes from, and we will see that actually a lot of mathematics can be derived from this paradox of the large denominator. So essentially, the conclusion is that usually in the fluid dynamics you can distinguish between two situations. One situation is called laminar flow. It's not a mathematical definition, but it's rather engineering point of view. So it's laminar flow refers to some kind of smooth flow. Where everything happens nicely. And it corresponds to low Reynolds number. So small Reynolds number, like bacterium flowing, everything is laminar. And turbulent flows is something very rough, something which happens. And that's important word, in fact. So high Reynolds numbers. And there is also the term which is now has a mathematical meaning, which is developed turbulence. And developed turbulence correspond to the limiting situation, which is when the flow is very turbulent. So the most turbulence is possible, and we see that turbulence, the only parameter that defines the behavior is a Reynolds number. Turbulence corresponds to high Reynolds number, so the only way you can define something clearly is taking the limit. So the limit of Reynolds going to infinity, which intuitively kills this term. But we know that we cannot remove it, just simply. So the Reynolds goes to infinity. Reynolds goes to infinity, as you see that it goes to infinity. It's not that it goes to infinity. It's just very large. And depending on situation, it may be very, very large. And it's very large. So usually people say that viscosity goes to 0. So you can have the same situation. You have in dimensional equations, remember you have viscosity on this place instead of 1 over Reynolds. So putting Reynolds to infinity mathematically is the same as putting viscosity to 0. Though you remember that viscosity never goes to 0. Viscosity is just always fixed. It's Reynolds goes to infinity because the system becomes large. But it's okay. So it's kind of vanishing viscosity limit. So, and as I said, that this limit formally sends Navier-Stokes to Euler. But this is with a big question. Okay, and now the two questions that we will gradually resolving. So you already can ask two questions. So first, somehow the system looks to be rather simple. You have a equation and just one parameter, and in a specific situation, like with a cylinder, it means that if you just solve it for all values of the parameter, you are done. So nothing to do. So the system looks rather simple in the sense that you have a well-defined equation with just one parameter, and just scanning all values of this parameter, you solve the problem. Of course, it's important from engineering point of view because this is what has to do with design of all vehicles and so on. But from mathematical point of view, it kind of looks boring, right? So what is the fun to solve one specific equation for all parameters? So the first question is why this is interesting. Why this is interesting for mathematics. So I already said that, of course, there is a millennium question whether this system has a unique solution. Right? So there exists unique solution to this problem or not. Though the answer is most likely yes. So it's kind of the technical question how to prove something which most people expect that the answer is yes, like Fermat theorem. So what is beyond this? So what are the other mathematical questions that, so let's assume that it's solved. So what are there any other mathematical questions that are interesting? So this we will be discussing during the course. And of course, if we solve it, so we will be talking about what are these problems? What are the interesting problems? Of course, this is absolutely subjective, so I will be talking about what are interesting problems for me, no, of course. Okay, so now I wanted just to show you some collection of photographs and videos just to see what happens. What happens with the flow in this situation. If it works, it worked. Okay. I just made some search in YouTube today in the morning, so just I picked up some videos, so you can do it by yourself later. So the first will be about flow, about cylinder, and I was trying to pick up videos not for numerical simulation, but from real flow. You know? So it's actually, the interesting thing is that for large Reynolds numbers, we will see why the numerical way to see what happens is rather limited, even with the supercomputers and so on. So actually the best way to see what happens is to see real liquid. And this is...
And that took 15.7 seconds to go 2 meters. That works out to be about 0.13 meters per second.
So there is a flow.
We're going to be looking at flows around a fairly simple shape today, namely a circular cross-section that's provided by this PVC
so the cylinder.
pipe. We're going to be immersing the PVC pipe in the flume and looking at how water flows around that. Now, an important part of the Reynolds number is the diameter of this, and in this case, the diameter of this PVC pipe is 115 millimeters.
So there are two different pipes, two different sizes, which changes Reynolds number, of course. Because Reynolds, it what comes. So the speed is fixed, or liquid is fixed, so you can change Reynolds number by changing radius.
This small pipe will give a Reynolds number about 1/10 the Reynolds number that we get with
exactly what it tells.
We're going to visualize flow using a stream of fluorescein dye, which fluoresces bright green under an ultraviolet light. Here, we're injecting dye from a small tube positioned just upstream. You can clearly see the streamlines as the fluid flows around the large tube. You can also visualize the quite complex flows that result. Here, we're dealing with Reynolds numbers up around 15,000 or so, which is the range where turbulent flows are quite common. Let's now look at these flows a bit more closely. Turbulent flow around the cylinder has three major components. At the cylinder's leading edge, there is a zone of relative stagnation as the upstream flow encounters the cylinder and is temporarily brought to rest there. As the water flows around the cylinder's lateral surface, the flow is laminar and smooth. Finally, just behind the cylinder's lateral face is a so-called zone of separation, where turbulent vortices are generated as the laminar flow just upstream separates from the cylinder as parcels of fluid in rotational motion. The separation occurs in part because the fluid behind the cylinder's trailing edge actually is moving in the opposite direction to the prevailing flow. When this retrograde flow encounters the prevailing flow, this imparts the rotational motion to the fluid, which separates as a vortex. The retrograde flow also produces a zone of relative stagnation behind the cylinder, seen in the accumulation of dye there. Now let's go to the smaller cylinder and lower Reynolds numbers to see what happens.
So this is when
with the smaller cylinder, we're dealing with Reynolds numbers on the order of about
just
2,000
starting.
or so. The wake behind the cylinder is still turbulent, but compared to the larger cylinder and the higher Reynolds numbers there, it is more orderly. Specifically, we see a phenomenon known as a vortex street, where turbulent vortices are shed first from one side of the cylinder, then the other. We also see vortices are retained behind the cylinder for a short time, then shed. If we drop the flow rate very low, we can bring Reynolds numbers down into the hundreds. There are still vortices being generated, but they now have an obviously laminar component to them. This means that viscous forces holding the flow together are now similar in magnitude to the inertial forces that initiate turbulence. It's even possible, with a few tricks with the flume, to drive Reynolds numbers for the small cylinder down into the tens and single digits. There is still a very slight rotational component to the flow, but the flow is definitively laminar, held together strongly by viscosity.
We saw at high Reynolds numbers that turbulent vortices are generated at the trailing edge of the cylinder. What we'd like to do now is to look at those flows near the surface a bit more closely. And to do that, we've rigged up a special device. It's a PVC pipe, just like we saw in the other video, or in the other segment. But instead, we now have a little port through here, drilled in the surface of the pipe, where we can eject fluorescein dye. And what we'll do is we'll put the pipe in the flume and we'll set it so that dye can be injected at the leading edge and rotate it around so that we can see how flows vary with the position of that port on the pipe.
Turbulence arises from the way pressure is distributed over a surface interacting with flow. According to the Bernoulli principle, pressure will be high and positive at the leading surface, but will fall to negative at the object's lateral and trailing surfaces. Negative pressures are particularly strong at the lateral surface. This imparts a complex flow in the same direction as the prevailing flow at the leading surface, but retrograde to the prevailing flow at the trailing surface. When the two flows meet, this imparts rotational momentum to a parcel of fluid. This is the origin of the turbulent vortex. Let's see if we can visualize these patterns of flow. When dye is released at the leading surface, we see it come momentarily to rest before it flows around the cylinder. The stagnation is evident also at the trailing surface. Note how the flow first is up and then down. This corresponds to the alternating generation of vortices that we see in a vortex street.
Okay.
At about 55 degrees upstream, flow over the cylinder is laminar and in the same direction as the prevailing flow. At about minus 30 degrees with respect to the prevailing flow, there is obvious retrograde flow from the back to the front of the cylinder. The separation zone is evident at about minus 40 degrees with respect to the prevailing flow. You can see the vortices lifting off the cylinder.
So what we've seen today is that when a fluid flows around an object, it flows around it in two very distinct ways. At low flow rates, you get nice smooth laminar flow over the surface of the object. But as you get to higher and higher speeds, that nice smooth laminar flow makes a transition to a more complicated turbulent flow. Now the transition from laminar...
Okay, I have more videos. Let's see what else I found. Oh, that's nice. The same, but a bit better coloring. So this is low Reynolds number. So you see this. This is still when it's all essentially laminar. So you see that there is a just something happens. Okay. This is what happens when you fly. Okay, next is this is increasing Reynolds number. This is nice video. So you take the cylinder, but it's now not circular, it's quadratic. That's okay. So very low. So again, you have this die. So you gradually increase Reynolds number and see what will be different. So this is slow motion. So this is purely laminar and stable. Slightly bigger velocity gives you instability. This is why you hear the electrical wires at high wind. It's exactly these oscillations. Yeah, these are three pictures shown together. So these numeric simulations for different Reynolds numbers. So 25, you see, so you will see differences. So the first is stable, then already slightly unstable, and then and more and more. Okay, so this is, I think that's. This is, I think, numerical simulation. Yeah, these numerical simulations. You can see. Of course, with numerical simulation, you have much better capabilities to visualize what happens. So this is much better visualization. So this is the complexity of what happens. So and this complexity is what drives the interesting mathematics here. Okay. What else? So the next, I also have some videos about turbulence in a pipe. So it's not, the flow is not around the cylinder, but inside. So this is a pipe, and then this is a die which is at low velocity, is just straight line. No? So it's carried by the flow, so everything is steady. And then you increase Reynolds number, so you see it's here in the corner. And at a certain moment, flow becomes unstable, just slightly. Yeah. And increasing Reynolds number, you see some periodic behavior appears. There is this bifurcation to periodic flows. And then it becomes completely disordered. So see, you inject some dye and it becomes fully disordered. So next is it's the same, essentially the same experiment, but just same type of experiment. Just showing the full tube. It shows what happens inside. Okay. Again, increasing the speed. And this I don't remember what it is. Oh. This is turbulence generated by the sides on some motors. This is more or less like experiment of Berenzer in Paris. And inside you have this very irregular flow, which is a turbulence. So this is properties of this flow is what we want to understand. Okay, I had some pictures, but okay. So let's do the small break, as usual. Break. And continue. let's start then. So, rest of the time today we will talk. I will discuss something completely basic that for people who are working with turbulence know very well. So the basic properties of the Navier-Stokes equations. Essentially, because these are important properties to which we will refer many times. So I will talk about this explicitly, especially for those people, for you to remember, and also for those people who are listening it from other areas. So basic properties. Of the Navier-Stokes equations. So what I would suggest you to do in any way is to read in parallel to read the book. So read for this piece. I will not follow this book in the rest of the course, but what will be talking now is to read a book of Uriel Frisch. Don't remember. About turbulence. I think it's called Kolmogorov's Legacy of Kolmogorov. And 1949, I don't remember. Okay, so doesn't matter. So there is this single very popular, highly cited book. So this is it. And read chapter 1 and 2. Chapter 1 and 2. Chapter 1 will be about this experimental part that I was showing you the videos, and chapter 2 is about these basic properties. So the first first part of the properties has to do with symmetries. So what we will be considering is, let us consider, okay, so we will be considering Navier-Stokes equations. Navier-Stokes equations. So I'll just write it again. Just put it in dimensionless form. And there are two things which are, and let's consider no boundaries. So ignore boundaries. Which means that consider it in the full space, full n-dimensional space. So what are the symmetries of this equation? So the first is space translation. Space translation means that instead of vector x, you can add any number. x0, any constant number. So in our space, and it will still give a solution. So what I'm writing, what means this arrow? It means that you define new coordinate, and you define new field. Depending on this new coordinate, which is the same as old field because u doesn't change. And then x prime can be, which is the same as the old one, but now you can express x through x prime here. So essentially what it tells that this is a gain solution. So whenever u is the solution, this is also a solution in X prime. And you can check it easily because you can just verify that if U satisfies this equation, that this also just substitute and see that it also satisfies the equation. So the reason is that because the equations of motion, they do not explicitly depend on coordinates. So any change of coordinates by adding constant number will still give a solution. So this is the second is similarly timed translation. So which means that you can add a constant to time, and this is essentially the same as evolution operator. So you just change time from one moment to another. And again, so what means that if U xt is a solution, then U x t minus t0 is a solution. Just in the same way. So it's, translation of both coordinates is a symmetry. So this is a symmetry. Symmetry means that the transformation that maps solutions to solutions. The next is already much less clear, trivial, is Galilean transformation. Very important transformation. And if you remember, Galilean transformation means that you change to the coordinates frame which moves with constant speed. So you change x to another frame which was moving with a constant speed u. And when you move to this new coordinate system, you see everything with a different speed, right? So it means that all speeds should change by this number. So this is for any given vector. So you go to the coordinate system, to the new coordinate system which moves with the speed u. So what it means? It means that if uxt is a solution, then so you have to add u, and also you have to shift the coordinates. So then it will be ux minus t plus u is a solution. So what you can do, a good exercise is take it and substitute to the equation and see that everything will cancel. So there will be two extra terms. One extra term will come from time derivative, because when you differentiate in time, you have to differentiate both arguments. So you get one more term. But at the same time, you have this nonlinear term. So this u will also give two terms, one with u capital, another with original u. And these two terms will cancel. So this is how you see that the equation is preserved. The next is parity. And parity means that x can be changed to minus x, and u can be changed to minus u. To change sign. And that's somehow important because this has to do with, in 3 dimensions it's important because parity is what maps left hand to right hand. So if you change coordinates to x to minus x, your left hand becomes right hand. And you can never transform them just by rotation. So you need parity. So this is nice transformation. The next is only for Euler system. So when viscosity is 0, so no viscous term, then you can also have time reversibility. So it's T to minus T and U to minus U. So it means that for Euler system, if you have solution going forward in time and then take the same dynamics going backward in time and changes the sign, it will be also solution. So there is no difference between the future and past in that sense. But for Navier-Stokes, this is not true. So Navier-Stokes clearly recognizes where is future, where is time, because of the viscous term. Then there are rotations. So rotations, how you define rotation? Rotation is defined always through the orthogonal matrix, so AX. And you have to, when you rotate coordinates, you also have to rotate velocities. So rotation means that A is a, so A is a matrix of rotation. So what if you remember linear algebra, so it should be orthogonal. And with a determinant, positive determinant, not -1. So this is matrix of rotation, and essentially it gives you new solutions in the form AU, A minus 1xt. So for any matrix, this transformation gives you a solution which also satisfies Navier-Stokes equations. The next is special scaling. So the next are scalings. So two scalings. So the first two scalings will be for Euler only. Euler only. So the Euler equations without viscosity has two scaling symmetries. So the space scaling and space scaling is what? So you change x to lambda x and u to lambda u for any lambda positive lambda. So essentially what it means that it doesn't matter if you measure in meters or you measure in centimeters. It's the same equation, but only for Euler, because the viscous term, for viscous term, it does matter. And the second is time scale. So something rather similar. So t goes to AT, but now u goes to AU divided by A. So it's a similar thing whenever you measure in seconds or in hours. So it's still the same equation, but only for Euler. So you can put it together. And one of the conventional ways how to put it is you take the triple UXU and you change the scale in the following way. So you take lambda 1 minus h t, then lambda x, and lambda h u. So you can see that these two scalings, from these two scalings, you always can compose the scaling of this form. So this is for any lambda positive and any h real. So the reason why in turbulence it's typical, it's popular to write it in this form because it has to do with some scalings that we will have. So, but essentially, it's a combination of the two. So now for Navier-Stokes. For Navier-Stokes equation, so this kind of transformation does not preserve equations because this kind of transformation leads to the change of Reynolds number. And you can check that, so the exercise. So check that whenever you do this transformation and change the Reynolds number, like this, then you have a symmetry. So if you change coordinates, speeds, and Reynolds number, you get the same equation. So you have a scaling, you have both scalings in Navier-Stokes if you also rescale your Reynolds number. So in particular, you will see that it is an exact symmetry, scaling symmetry. Of Navier-Stokes for h equal minus 1. If h equal minus 1, Reynolds doesn't need to change. So if you, it means that, so h minus 1 gives you lambda squared. So if you take for any lambda, so if you take lambda times different, so if you change the way how you measure length by lambda and how you measure time by lambda squared, the Navier-Stokes is still invariant completely. Okay, so that's it. So this is a collection of the symmetries. These are not the all symmetries that we in principle made. There are also some other symmetries, but these are the symmetries that the principle and the symmetries that we will be using. Okay, so this is the first part. So probably the good exercise is proof the symmetries. Okay, the next set of properties has to do with conservation laws. Conservation laws. So something is conserved. So here we go to mainly for convenience. So we go to some to the formulation which is even more abstract. So essentially, we consider flow in a periodic box. So this is a rather unphysical assumption which most of the theoretical people in fluids do is the following. So boundary is always a problem. So if you can try to understand turbulence, there are two rather different questions to understand turbulence far from boundaries and turbulence near the boundaries. So you would like to decouple these two questions. So just like if you study the turbulence far from boundaries, not to have a boundary. So if you want to get rid of the boundary, you can, in principle, consider the flow in infinite space. But then you face another problem, because infinite space is also trouble, because it's not compact. So you have, it's very large, so you have problem with integration and everything. So how to, on one side, have a compact space, and the another side have no boundaries. And this is the way how to do it is a periodic box. So what you do is you consider a periodic box, so cube with a size L. And now you assume that it's periodic. So the upper part is, so whenever particle goes away from, so there is no boundary at all. So particle can pass through it, but whenever it passes through it, it is transported on another side. So this is the way. So essentially, the condition is that, mathematically written condition is that u at xt, you identify it with u of x plus L ei t for all. So ei is a unit vector in direction I. So you identify speeds at all opposite faces. So this is a way, so in this way you have a compact space, which is actually a torus. So it's exactly the torus what we know is mathematics. So it's a torus in 2 dimensions. For example, if you identify the two sides on different sides, it's topologically torus. In 1 dimension, if you identify the opposite points, it becomes a circle. So topologically, it's a circle, 2-dimensional torus, 3-dimensional torus, and in fact, there is no boundary as it is, because whenever particle passes through, it doesn't feel any change, kind of boundary-like. So it's just normal Navier-Stokes equation. So there is no, on one side there is no boundary, and on the other side the space becomes compact. So this is what we'll be considering. And the immediate consequence of this fact is that you can easily compute averages. And rather simply compute many rules like conservation laws, for example. So averages, so space average. So whenever you want to take space average of some function f of x, which is in periodic box, so we call it, usually you call it Tn. Tn means that you're periodic in all directions. So any function of periodic in Tn, so is, so we'll denote it by this angular bracket. So it's just integral in a torus. And the integral is good. If the function is good, the integral is so is the function, for example, is if it's continuous, you have always finite integral because the torus is compact. So you cannot have problems with divergences if you, which you would have if you have n-dimensional real space. Of course, if it's average, so we should divide it by the volume of the domain. Okay, so the simple exercise is to show different identities which just directly follow from the periodic boundary conditions. So show that, for example, that if you have any derivative, if the function average of any derivative is 0. So this follows from, because when you take an average, you integrate with respect to xi coordinate. So it's equal to differences between of function f at two sides, but it's periodic, so 0. And from this, you immediately get other conditions. So, for example, this. This is because this is a derivative of a product, right? So this is obvious. Then you can derive some more complex identities. But which essentially have the same origin. This is you write down all derivatives and then pass one derivative one by one through this condition to G. Then there are conditions of the slightly more complicated form. So for example, like this, about curl. So I essentially took it from Frisch book, so you just take a look at it. And then also there are some conditions which are very useful, which take into account incompressibility conditions. For example, you can combine these properties with incompressibility condition. So the scalar product of any field with Laplacian, you can equate it with average of scalar product between two curls. And this is true if the second field is incompressible. Just you can try to derive this or derive your own conditions for the periodic box and incompressibility condition. So the first conservation law is the conservation of momentum. And this is simply the fact that the average speed of the full fluid, average speed of the full flow does not change in the cube, periodic cube. So proof is, let's just directly prove it. So how you do? So derivative of average, see average is an integral, so it's a linear operation. So whenever you take derivative, you can put derivative inside the integral. It becomes partial derivative. Then you can use Navier-Stokes equations. It becomes minus u grad u minus grad p plus and we can just kill it term by term. So the grad p is derivative. So already from this condition we know it's 0. Laplace average of the Laplacian are also derivatives, right? So each term is a derivative of something. For the same term, reason is 0. And finally, the convection term so what you do, you open up the expression. So it's sum over components. So it will be ui d u dxi, right? So now you can use this formula to pull derivative on the first component. It will give minus right? And now this is 0 by incompressibility. So this is 0. So which means that this is 0. This is what we wanted to prove. So rather straightforward. The next is conservation of energy. Conservation of energy. So let's see what it is. So what we need, actually what we will need in the derivations is, so we call energy is mean of the square of the speed over 2. So it's actually modulus square. So it's called energy. And together with the energy, let us define another quantity, which call omega. And it will be defined in a similar way, but through the vorticity. So it will be called entropy. So the statement is that dE dt is equal to minus 2 nu omega. Or in dimensionless form, minus 2 omega over n. So that's what we have to prove. And this is, of course, for the Navier-Stokes. So why it's called conservation is because if, in case of Euler equations, so when the viscosity is 0, so you have direct conservation of energy. So derivative is 0. So energy for Euler should be conserved. It's good to see how it's proved. So let's just prove it. Okay. So what we do, we take Navier-Stokes and multiply it by component ui and sum with respect to I. So what will be term by term? So term by term, it is ui d ui dt. So let's take each component of Navier-Stokes. Okay, so the next is ui. And then remember that second term is what? Second term of the Navier-Stokes is U grad. So U grad is a Uj by d Ui dxj, and then this is the sum over ig. So this will be the second term. Just check it is like this. Then it will be pressure term. So remember. And then there is a there is Laplacian term, so it's 1 over Reynolds, sum over I, but then also G. So there is a Ui d2 Ui over dx g2. So this is the form. Okay, so next we take average of all the terms. So we have condition for averages. And let's take it term by term. So the average of this term. So you already can see that this is derivative of u squared over 2. So this will be d dt over 2. And then you can take derivative outside, and what will be left is energy, right? So this will be first term. The second term so what you do is, again, you combine Ui together. So it will be Uj d dxj Ui squared over 2. Now you put derivative to another side, remember, and you can do it from this relation, and it will give you minus. But now since you sum up this with j, this gives you 0 because of incompressibility. Because this is exactly incompressibility condition, so this is 0. So more terms. So this is also 0. Yeah, because you pull derivative on the other side. Again, incompressibility. So you see, incompressibility condition helps a lot. And finally, this term. So I will not do. So it should be equal to exercise. So show that this is equal to minus, so it should be with minus, no? So it should be minus 2 omega, yeah? Which is minus average of omega square, where omega is a vorticity. So this is a long and boring derivation, so you should just pull derivatives from one side to another and just to see that this will come up to this equation, to this property. And here you will be using both the fact that you can, because of periodic box, you can switch derivatives, and you have incompressibility. So this will end up the proof, because it's because the two terms are 0. This is derivative of energy, and this is derivative minus 2 over Reynolds of derivative of entropy. Okay. I will also sketch. So there are two more conservation laws, which I will give it without proof. We will not use the first, I think never, in the course. So in 3 dimensions, there are, so when n is 3, right? So there is a conservation of helicity. This is a very interesting mathematical quantity, which is defined as a mean average of the scalar product between the velocity and vorticity. So vorticity, projection of vorticity in direction of velocity over 2. And actually, it has to do with topology. In fact, you can connect this property with some topological conservation, which is somehow conserves knotedness. So somehow conserves the knotedness, no? Degree, I cannot pronounce it, of knotedness. So if you like knots, so this is exactly somehow measures how many knots in the lines of vorticity, in the vortex lines, are in your flow. And the equation is that for the Navier-Stokes equation, you have that derivative of the helicity in time will be minus 2 nu by the what's called HW. So HW is mean of the omega, so vorticity, times curl of vorticity over 2. So you see, it's essentially the same formula, but where you substitute velocity by vorticity. So it's called vortical helicity. Well, this is a bit messy, but important that whenever you have Euler, so in Euler is just directly conserved, because velocity is 0, so the degree of knotedness is directly conserved in Euler. So just remember that there is such a conservation law, but we will not use it. Another conservation law that I think we will use has to do with 2 dimensions. So 2 dimensions is a very nice dimension for fluid dynamics. Essentially because you have another law, so that in 2D. So when the flow is just on a plane. In that case, this is not true, so you don't have conservation of helicity. Essentially, not that you don't have. In 2 dimensions, they're orthogonal, so it's 0. Because u is in a plane, and omega is either, you consider it as a scalar, but if you want to consider it as a vector, it should be out of orthogonal to the plane vector. So, but what you have is conservation of entropy. So the same entropy that was controlling this change, the entropy which was controlling the change of energy in Navier-Stokes, but now it also in 2 dimensions it's also conserved. So you have such a nested conservation. So the change of energy is controlled by entropy, but now and conserved if you have inviscid flow, and now you have a conservation of entropy, which is written like d omega dt minus 2 nu p. So now p is, it's not pressure. P is, you have such a name. So it's curl of vorticity itself square over 2, and it's called poly. It's now starting to look like botanics, no? So it's many different notions with different names, but they're interconnected. Let's stop here. Okay, so see you tomorrow.